Yep.
Anytime you want.
Okay, so welcome everybody to the second tutorial in this year's DEBS. And so this second tutorial will be on blockchain consensus. And the full title is Blockchain Consensus Unraveled, Virtues and Limitations. And it will be presented by Suyash Gupta, Jelle Hellings, Sajjad Rahnama, and Mohammad Sadoghi, all three of the Expo Systems or Exploratory Systems Lab at UC Davis. And I mean, that's basically my part. I'm chairing this session. I think all of the speakers are open to questions during the tutorial because the tutorial will be live. So there's good way, or I mean, Kaiwen basically suggested people to ask questions just on by unmuting themselves, if I remember correctly. So that's probably the best way, or you can do on Slack. We'll relay that back to the speakers and ensure that all of the questions get answered. And with that, I would say I'll hand over to the speakers for the tutorial.
All right, thank you so much, Tilman. Thank you so much, Carmen. So Suyash, perhaps maybe we can start, sharing your screen. And so good morning, everybody. Thank you for coming this morning and attending our tutorial. So what we're gonna be talking about today is first, in the first half, Suyash is gonna give us an intro, and then Jelle is gonna give us a theoretical background in blockchain, in particular with consensus. And in the second half, and we will look at modern consensus protocol, and also going to look at some of the protocol that we developed at the Expo Lab in the last few years. And finally, we're all going to give an overview and a little demo of ResilientDB, which is a blockchain fabric that we developed at UC Davis from scratch. So with that, Suyash, if you lead the intro, please.
Hi, everyone. Thank you, Mo, for the introduction. And my name is Suyash Gupta, and we'll be presenting this tutorial on blockchain consensus unraveled, virtues and limitations. And at the time when we were writing this tutorial, we were trying to think, what are the important aspects that affect or surround blockchain system? And we were trying to present those ideas in this tutorial. So what is a blockchain? A blockchain, as we all know, is simply a linked list of blocks, and its key element is that it is immutable. Each block contains the hash of the previous block, and a block contains information about some client transactions. So why blockchain? Well, blockchain provides three important properties like democracy, decentralization, authentication. How does it provide democracy? Because it allows everyone to participate. Everyone has an opportunity to vote. It provides decentralization because it provides a replicate system where everyone can store their data and everyone has equal rights. And obviously it requires security because it is immutable. If I want to talk about blockchain, then I need to first discuss about what are the key components in a blockchain system. And in any blockchain system, following are the main components. It has replicas. Every node which participates in the blockchain stores exactly the same data. It has some clients who will be sending their transactions. And then there will be a protocol which will basically ordering these transactions. And that protocol is a consensus protocol. Obviously, we're talking about security, so there need to be some measure of how can we actually make these transactions secure. And that's why we use cryptographic constructs. And then there needs to be some place where all these transactions had to be noted down. And that is what we call as ledger. So the key component in our perspective in blockchain is consensus. And why is it consensus? Because consensus helps to order the transaction. So we have a client, and that client wants to send his transaction. And that transaction, he wants it to be executed. And to keep blockchain consistent, we want the transaction to be executed on all the replicas in the same order. And that is the aim of this consensus. But note here, in a blockchain system, there can be some people, some replicas who can be actually malicious. And if such is the case, then it is the responsibility of this consent protocol to ensure that all the replicas still order transaction correctly, even though this malicious person can do anything possible. So based on this direction, we can define blockchain systems in two categories. They can be permissionless or permissioned. We all know about permissionless blockchain system. The most famous example is Bitcoin. And what do these permissionless blockchain systems allow? They allow anyone to participate. And identities of the replicas are known a priori. The famous application of these permissionless blockchain are cryptocurrency, money exchange, and so on. And then there is another extreme, which is called as permission blockchain systems. What do these systems say? They say that only a subset of replicas can participate. Basically, any replica who's ready to share its identity can participate. But note that there is no assumption that these replicas need to be trusted. These permission blockchain systems are being used in many applications like healthcare, energy trading, and so on. So let's start with some of the famous permissionless blockchain systems. Just a simple overview. We all know about Bitcoin. What does it is? It is a cryptocurrency, a monetary token that is exchanged between replicas. It uses Nakamoto consensus, which is basically proof of work beneath its scheme. What it allows is permissioned access, anyone can participate. How does it work? Well, proof of work requires solving hard cryptographic puzzles. Any replica that wants to create a new block, well, in Bitcoin terms, these replicas are called as miners, and if any one of them want to create a new block, then it needs to solve a complex puzzle. And what is this puzzle? That is basically calculating a hash. It could be a double SHA-256. And as more and more miners join the system, and the difficulty of this puzzle has to be increased to prevent malicious attack. So clearly it can be seen it is very research high consuming because the puzzle has to be made more and more complex. And obviously it yields low throughput. Another famous application, Ethereum, it's also a cryptocurrency. It currently uses proof of work, but there's a plan that will move soon to proof of stake. And what is the key benefit of Ethereum over Bitcoin? Well, it allows something called as smart contracts. Different programmers can write their own smart contracts. These smart contracts, in my sense, are basically similar to procedures in databases. And the key limitation of Ethereum is that these contracts have to be written in Ethereum's own language. So there's a hard dependency on usage of Ethereum virtual machine. Ethereum also plans to expand its system to permission applications. But what is the problem with these permissionless blockchain applications? Well, the first main problem is that a lot of them allow existence of forks in the blockchain. How? Well, they are using proof of work and they allow multiple miners to basically mine at the same point of time. And it is possible that two or more miners might find the hash at the same point of time. And then there's a rat race that whose chain or whose block will be accepted by others first. And there have been series of attacks which are very known. That's the whole reason that there's a fluctuation price of all of these applications. This is why there was a start of permission blockchain systems, where basically the whole idea is that there will not be a fluctuation of forks something. Anyone who wants to participate needs to share its identity. And these protocols rely on traditional BFT protocols. Basically, these traditional BFT protocols are not computation intensive. The whole reliance is to use communication primitives. And recently there have been a series of applications using this permission blockchain system. A lot of blockchain databases have come recently, and all of these use these design principles. We'll look in depth about permission blockchain systems later in this presentation. So The key focus of this whole presentation would go around a word called as transaction. And what is a transaction? A transaction is simply a transformation from one consistent state to another. It is like a contract between two parties, a sort of a marriage. Transaction is like a set of read and write operation. There are several types of transactions like nested, compensating, multi-operations, so on. For every transaction that has to be executed, we expect 4 properties to be followed. We expect atomicity, consistency, isolation, durability. And there's generally seen a sort of a struggle between consistency and availability. Availability says that database needs to be always available. And a solution to solve that is to use replication, make multiple copies of the database that promotes availability. The problem is that these might fail. There can be attacks possible. While consistency says that database needs to be correct. Basically, we have made all of these copies. Now, each of these copies needs to send exactly the same data. Well, maintaining consistency is expensive. So you can see that both of these properties, consistency and availability, lie in diametrically opposite direction. Now, why are we discussing these properties? Well, now in this presentation, we'll discuss about how consistency will be used to basically order these transactions. And as we said, consistency is the key component of this whole blockchain environment. So this availability and consistency, you'll see that there's a clear struggle there. Now I'll give the next to Jelle because he'll continue with the rest of the presentation.
Is the sound working?
One thing, so one also, Jelle, maybe before transitioning, if anybody has any questions, and again, please, anytime throughout the presentation, let's make it as interactive as possible. Ask any question that you may have.
I also will have some parts where I will switch from one topic to another. So at that point, I shall also ask for questions. That's the easiest point. There's nothing, then I would say that we can continue. So I'm going to talk a bit about the theoretical background for consensus and for blockchains in general. Of course, I'm going to do that in a very biased way because we are looking for consensus for a very specific application. So we will look at the theory from that perspective. So let's start. Let's see why it works. So what we are working on in our lab is to try to get a data processing system or a transaction processing system that is resilient. So it can deal with failures while also providing basic normal database operations. And if we do that, then we can ask ourselves why we want that. The second question that we're going to ask is, well, what is available? What does the theory say that we can do, what we cannot do? Then the third question is, of course, where does our research come in? Where can we improve to make such a resilient system happen more? And finally, based on that, we can see, okay, we are missing some technologies, and that's what we can develop here. So let us first look at the why. And it needs to be said here that we're going to focus on permission blockchains. So we know all participants. The reason for doing that is because permission blockchains allow us to have very high throughputs, very low latencies, whereas permissionless blockchains like Bitcoin have much worse performance. Furthermore, it also is a bit easier to support different kinds of tech models in a permission blockchain. The downside to it is that managing the blockchain by adding replicas or removing replicas is a bit hard, but well, everything has its upsides and its downsides, I guess. So first thing I'm going to look at is why we want this high performance resilient data processing. That's quite easily motivated by normal motivations for database. So if you have a normal database, one of their key components is that they are resilient to crashes. So whenever they crash, well, that can happen, but we can always recover the state of the database back to something that makes sense. And this gives database a clear advantage over just doing manual file use, for example. But the next step is, of course, can we also assure that our system can deal with crashes without having to recover? So when something crashes, we just keep on providing services. This one more step basically can be achieved with Paxos, which is a very simple crash resilient consensus type of system. We even want to go one step further. What we want is a system that can deal with crashes, but also with malicious behavior of some of the replicas, or with software failures at some of the replicas and stuff like that, while still be able to provide services. One clear direction for wanting this is if we want to provide database services in a federated environment with many different participants, then it's going to be hard, for example, to assure that all participants have the same software at all times. They might have updates, they might have network failures. And during that time, we of course still want to provide services. So from our point of view, going towards Byzantine resilient systems is just an evolution of database systems in an even more resilient direction. And the other question is, why do we want high performance? I don't think we really have to answer that here, right? We all know that data is ever growing. And besides that, we also know that not just the data is growing, but also the amount of computations that we need to do on this data to do something useful with the data is also sharply growing. So if we want to have a data processing system, then we sure as hell need to assure ourselves that's going to be high performance, that's going to be scalable. So that's the simple of why we want it. So then the next question is, if there is any questions of the public, let's first see if that.
So we have one question in the chat
Okay.
from Kaiwen. So I'll read it. Could you justify why 3PC is classified as crash recovery? From my understanding, the third phase is used to avoid blocking when a crash occurs. So wouldn't that be a recovery?
Well, in this, of course, we have to categorize it a bit, right? 3PC can deal with some crashes, but not with all. It can deal with a few more crashes than 2PC, but it wouldn't be able to, well, it doesn't have the crash recovery that Paxos provides. So it's on a growing curve, right? So we have to make a picture that makes some sense, I would guess. Well, oh yeah, we're going to talk about what do we already have at the moment. We have quite a few things. So the first thing we have, because this entire presentation is about blockchains, we have blockchains. And a blockchain, for the purpose of our kinds of system, is basically a resilient tamper-proof ledger, which is maintained by many participants, by many replicas. With a ledger, we mean basically an append-only sequence of transactions. So in database terms, that's just your journal or your log. We also want it to be resilient. So whatever happens, we want it to be available. If a replica fails, nothing changes. We just want to keep on providing services. And we want it to be tamper-proof in the sense that no replica can just change what's in the ledger without participation of all the other replicas. And in this sense, blockchains are just a very standard distributed, fully replicated systems. And these have been studied for quite a while. So we know what's possible, we know what's not possible in these systems. What do we also have? Well, one way to maintain these ledgers, because we want to be able to add stuff to the ledger. And we can do that with consensus protocols like PBFT or Paxos or proof of work and permissionless systems. And these consensus protocols, from a theoretical perspective, their main goals is to assure that if you're going to start accepting our transactions, at some point every replica will accept some transactions. That's called termination. And we also want, of course, that all the replicas can accept the same transactions. That's usually called non-divergence. Of course, in a practical system, you want a bit more because you're not just accepting transactions internally. You want them to come from some clients, and you want these clients to be able to find out what's happening. So we usually also add 3 more requirements, namely that the transactions that we accept are valid. They come from some client, and that client actually wants that transaction. We want to assure that the clients get a response, that they can learn about the outcome of their requests. And of course, we also want to assure that if a client wants to perform some request, that it's going to be able to do so at some point, so that faulty people cannot just block some clients. And a picture that's quite easy to describe. We have a client C, has a transaction. The client sends that to the system. The system does some magic behind the doors that's called consensus. And after that, every replica in the system has that transactions, execute that transactions, and informs the client of the outcome. Then, of course, if we say consensus is going to provide us a blockchain, we also quickly need to describe how we do that. So blockchain is usually just a cluster of replicas. All these replicas hold a copy of the ledger, and these replicas use consensus to decide for every round which transaction they're going to add to the ledger, and also execute and inform the client. Of course, to assure that this all works out in the end and that all replicas will keep on having the same state, we also need to make another assumption on the transactions, and namely that they are deterministic. So if you give me an exact transaction and some state, then no matter what happens, every time when I execute that transaction on that same state, you're going to get the same outcome. Otherwise, you might see that two replicas execute the same transaction, get a different outcome, and then, of course, we have inconsistency in the data, so we don't want that. So those are the basic ingredients that we have. The question is then, what else do we have? Well, if you look at the theory, you can find some variations on consensus, like Byzantine broadcast, interactive consistency. There's a lot of theory on the costs of consensus, how fast we can do it, and that kind of stuff. We have some practical consensus protocols like PBFT. For the rest, we have a way to store these ledgers so that they are tamper-proof and that individual replicas can show that they have the correct version of the ledger. Of course, the way to do that really depends on your application and on how you do consensus. And to support all of these things, we have a lot of cryptographic tools. But if you look close at this list, we haven't said anything about providing high performance. So there's no techniques yet to provide scalability of stuff like that. We will look at that a bit later on how to provide it. The first three things I will now look at is the theory on PBFT and the variations of consensus, because those are also the available tools on our toolbox to make high performance resilience data processing happen at some point. So the first variation of consensus is a simplification. It's the Byzantine broadcast problem or the Byzantine generals problem. And instead of an outside source of decisions that are broadcasted throughout the system, we say, well, one of the replicas can propose values, and if that replica is correct, then all other replicas will accept these values. If that proposing replica is not correct, then the outcome might be undetermined. Everyone might accept something, but it's not necessarily a sensible value. And in this sense, it's a simplification, because as soon, of course, as the proposer is correct, then we can use the proposer to basically do the consensus step. But if it's not correct, we need to wait to deal with that. On the other hand, we can also look at interactive consistency, which is much more complex than consensus. And in interactive consistency, every replica has its own values. Then it does the interactive consistency step, and afterwards, all replicas learn about all the other values of all the other replicas, and as long as the replicas that propose the value is correct, all the other replicas will have its value. And if a replica is faulty, then, well, the outcome on its value can be anything. Of course, this can also quite easily be used to solve consensus, because in that case, everyone would just say what they think they should accept, and then we can do majority vote on that. So in that sense, it's more complex than consensus. Then, if we look on consensus and the broadcast problem and on interactive consistency, it has been studied quite a lot and a long while ago, so we know how complex these are. So let us look at these results. And the first theory bit is you can just look at what is able in a distributed fully replicated system. And a few years ago, a lot of that has been summarized via the CAP theorem. that says if you want to distribute a fully replicated system and you want it to be consistent so that every replica has the same data, you want it to provide availability so the system provides service continuously, and you want it to be able to deal with network failures or with network disturbance as well. What the CAP theorem states is if you want these properties, then you have to choose some out of 3. In most cases it's 2 out of 3, but of course it depends a bit on the type of system and how it's going to work out directly. The only problem if we apply this to blockchain systems is that the CAP theorem of course uses a very narrow definition of what consistency, available and partitioning is. And this definition doesn't always agree with what your practical system provides. To see the CAP theorem in practice for a blockchain system, well, if you have a permissionless blockchain like Bitcoin and stuff like that, they're really about open membership, about being able to join and leave. And that focus really is on providing availability and providing partitioning, because if you leave, of course, the network gets disturbed and you want to provide service all the time. The downside of that is that in a permissionless blockchain, you will see that the data is not always consistent. So some replicas might be on one fork, other replicas might be on other fork, and only in time they will reach some consensus on what the actual state should be if everything goes correct, but that's not even a guarantee on that. The permissioned blockchains that we look at, their main focus is just on consistency. No matter what happens, all replicas should have a consistent state. To provide that, they have to sacrifice either availability or partitioning. And in practice, we see that these systems choose to provide availability as long as the network is good enough. So they can do with a little bit of network failure, but if the network fails too much, then the system just stops. But at all times, you have consistency. So that's where we lay at. The CAP theorem is of course very general purpose. It's not really focused on consensus-based systems. So let us now look a bit more at those systems. Unless there are questions, because this was something popping up. If we're going to talk about the theory of consensus, then the first thing we need to make is some assumptions on what our system does. The first assumption I can make is, can it deal with crashes? So can it deal with participants that just stop operating? Or can it deal with more than that? Can it deal with Byzantine failures, with software errors, with malicious behavior, with coordinated malicious behavior? And based on that, well, to deal with that, we always have to make some assumptions on the underlying system. So one of the basic assumptions is that no matter what happens, if all replicas would crash or all would be faulty, of course, we cannot do anything. So we need to assume that some fraction of the replicas behave correctly. Usually in permissionless systems like Bitcoin, the fraction that is correct is determined by a majority of the resources they own, the computational power, and stuff like that. In permission systems that we look at, it's really determined by a majority of participants needs to be good. And of course, in many practical systems, we also make some assumptions about cryptography and that cryptography is safe and stuff like that, because otherwise it's also going to be very hard to do anything. Having said that, the next choice we can make in our system is to choose between designing for synchronous communication, which is relatively easy. We assume reliable communication with bounded delays. It really allows us for replicas to detect whether other replicas are communicating or not, because, well, you know, if that replica wants to communicate, you can get your message within like 10 milliseconds or stuff like that. In practice, most systems do not have synchronous communication, they have asynchronous communication. It can be unreliable, messages can get lost, they can get delayed, they can get duplicates. But it also poses a challenge, because if you look back at the theory, then we know that in an asynchronous environment, we cannot even deal with a single crash. So if you want to make a practical system, then we already know it's impossible. So what are we going to do then? And the standard solution that a lot of permission systems make is, okay, we're going to assume a synchronous communication. We know it's not possible in that case. So we're going to sacrifice something. And what they do is they always are going to provide consistency of the data. That's the main goal. but they can only provide availability, so they can only provide services as long as communication is good enough. And good enough is usually close to reliable, but maybe 1 or 2 replicas are down, something like that. And that's a practical setting, it works, so that's what we do. Then the next question you can ask yourself is, how are we going to assure that replicas can communicate in a way that they can authenticate from which replicas are sending messages, which replicas are receiving messages and stuff like that. And to do that, we have 2 choices. We can use public key cryptography. We can just say every replica has a public private key pair. They sign all the messages. So if I receive a message, then I can check the signature, know from who it comes. This makes it also really easy to deal with forwarding messages because, well, no replica can tamper with a signature without that being detected. Also has a downside. Digital signatures are expensive. So some systems use simpler message authentication codes, but those can basically only be used to say one replica sends to another replica, and that replica can determine, okay, I got it from this one replica, but that receiving replica cannot then just send a message to someone else while maintaining the claim that it came from the first replica. You can choose between the 2. The only difference between the 2 in practice is that if you want to be able to deal with only a few good replicas compared to a lot of faulty replicas, then you need digital signatures. Because in normal protocols, you're going to need more than 3 times as many replicas than faulty replicas. But if you have digital signatures and reliable communication, you just need good replicas. In practice, it's a bit more nuanced, because in practice you just not want your system to be able to do consensus. You also want clients to be able to learn the outcome, so usually you need a majority of good replicas to be able to do that. Then the theory also provides us with a lot of lower bounds on communication and on the number of messages. And most of these lower bounds are stated in the number of faulty replicas. So if we have at most faulty replicas, then we know that in the worst case, our consensus is going to require F+1 phase of communication. And usually these phases are broadcasting phases or stuff like that. We can also do something that's not as pessimistic, that tries to optimize for the number of faults that we actually have. But in that case, we're going to need the number of faults plus 2 phases, if any failures happen. That's, of course, the number of phases that we need to do one in a row. We can also look at the number of messages that we need to exchange. And there the theory says, well, of course, if we want to reach consensus among n replicas, then of course we need to send n messages, because every replica has to learn at some point which value they need to reach consensus. And to deal with the faulty behavior, we need an amount of messages that is quadratic in the number of faulty messages. So this already shows that no matter what happens in the worst case, consensus is going to be expensive, even if we have the best protocol implemented in the best ways. And that's unfortunate. What can we also say? Well, there's also some theory on how the network should be connected. And this basically states that the network needs to be well enough connected to allow most replicas to talk to each other. If we don't have that, it's also going to be hard, because then, of course, we cannot really distinguish between network failure and replica failure. But let's not go into too much detail. So to summarize on all this theory, what we have seen is basically consensus is going to be expensive. We're going to have a lot of replicas to deal with some failures, namely 3 times as many replicas. In the worst case, we're going to have a lot of communication phases to reach consensus on a single value, and a lot of communications to do so. Beyond that, we also need a really well-connected and reliable network to just even start building a system. And as I said, this also already shows that if you want to reach something scalable, there's just another limiting factor on the performance. So we need to deal with that. I think this is a good point for some questions if there are any.
Hey, Jelle, just a question about, so what you show here is a theory of specifically for practical consensus algorithms. So how does anything like Nakamoto consensus based on proof of work fit in this? Because I don't think the n greater than 3f applies to Bitcoin, for example.
Yeah,
so how is that reconciled?
Bitcoin is a bit of course, Bitcoin doesn't use the theoretical definitions of a consensus system that they used in the 80s. But if you want to translate Bitcoin to the setting of consensus that they studied, then of course, the first thing you're going to say is it a synchronous or an asynchronous system? And the easiest way to look at Bitcoin actually is as a synchronous system, because if you don't want it to have forks, then all replicas need to be aware of what all the other replicas are doing, otherwise you can't have forks. And the ETHEREUM consensus just doesn't allow forks. So synchronous system. Then proof of work is very heavily reliant on digital signatures. All communication there is signed. So we have a synchronous system with digital signatures. Then of course the third assumption that we need to make is how are we going to translate majority by resources to what the theory says, because that's always in the number of votes. And for proof of work, we can say, well, what if everyone just has the same amount of resources? Then one vote is one resource, right? And in that sense, if you would apply these assumptions on proof of work, then you would reach a state where apparently the number of replicas that are good need to be more than the number of faulty replicas, which is sort of in line with what proof of work in practice also requires, and we need a majority of the resources to be in good hands.
Okay.
But of course, it's a bit, the comparison doesn't hold up entirely, because the system assumptions between Bitcoin and between what the theory people studied are slightly mismatched. So you have to do some hand waving there.
So thanks for that. So are you aware if there's also a body of work that studies these impossibility, proof theorems and stuff like that in a model that's closer to practical blockchain, or it's really more focused on this theoretical consensus, assumptions?
There are some papers on that, especially when proof of work just came out. There were quite a few of papers to show that it was basically just consensus, or to limit it or to connect it to consensus. But to be honest, I have not really found a great paper that makes a really clear case and explains all the details yet. So I think for both the Bitcoin community and the permissionless blockchain community and the theoretical distributed community, there's quite some room there to just get a nice server paper to basically connect these parts completely and just cover every aspect of it. I think that's still slightly open. But in the basics, we know that proof of work works, and we can connect it to what already happens in the way I just explained.
Okay, thank you.
Then we've already talked quite a bit about just theory. So let us put that theory a little bit of practice by looking at how a practical consensus protocol operates. And we're going to look at PBFT. It's a bit older, it's from the 2000s. But PBFT is a very good starting point if you want to understand any other consensus protocol, because a lot of them built on the design of PBFT. And PBFT, what it does, it uses a primary backup design. It assumes that the primary is going to coordinate everything, so it's going to propose transactions, whereas the backups are trying to see whether the primary is behaving correctly. So you can basically see PBFT a little bit as the Byzantine broadcast problem, plus some verification steps to assure that the broadcaster is doing its work correctly. And we have also a small sketch here of how the communication would work. Of course, all the magic happens in the green part where we say replication and verification. That's actually the core of PBFT. So let's look at how that works. So here we have a client, sends some transactions T, sends it to the primary P at the moment. And then the first step that this primary does, it's going to decide, okay, we're going to execute this transaction as the road transaction. It's going to propose that to all the other replicas in pre-prepare message. And then the next step for all other replicas is to determine whether they all got the same message from the primary, because otherwise the primary is faulty, of course. How do they do that? Well, they exchange what they got via prepare message. And after I receive a lot of these prepare messages, I can decide, okay, most other replicas got the same thing as I got. So I'm confident in the working of the primary. I'm going to commit this, and then I can start executing that. What does it mean, most of the other replicas? Well, we know that F replicas might be faulty. They might not send anything. So we wait for n-f identical prepare messages. After we receive those, we can commit. We do that also via commit message, so that all the other replicas can also determine that we all do the same thing still. And if that's correct, goes correct, then everyone executes. They inform the client about execution. Then a new transaction is accepted. That's how the normal case works. Of course, we also need to deal with many faulty cases because the primary can do something wrong. So let's look at that next. But before we do that, we can quite easily show if communication is reliable, then this normal case will just do its work. It's quite efficient. It's good and it will accept the transactions. Next, a faulty case. So one of the things faulty primary can try to achieve is say, well, I have two transactions. I'm going to propose two different transactions to different replicas. Let's see what happens. And in this case, the primary proposes a transaction of the first client to two replicas and of a second client to one replica. Well, they will do the prepare step because they only got the single transaction. But after the prepare step, each replica has to do some counting to see how many prepare messages they got. And based on that, they decide which value they're going to commit, if they can commit. And in this case, well, replica 1 and 2 both got three messages saying that client transaction 1 should be executed. So they say, okay, we're going to commit to that. But the third replica got something different, and the third replica is stuck. So he cannot do anything. And after committing, the first and the second replica still think they're on the right path, so they execute and they inform the first client. The primary still is bad and he executes something else and informs the second client. So what happens in this case is that the first client sees two replies and he knows there's one faulty replica. So one of these replies must be from a good replica. So the first client says, okay, my work is done, my transaction is processed. The second client only gets one reply. That's not enough for the second client to determine whether that was good or bad. So the second client says, okay, nothing happened. But here we have a problem because, well, the third replica doesn't know what's going on. This first and the second replica executed something and the primary is just making a mess altogether. So we need to deal with this in some way. Let's look how we can do that. But before we do that, a very important property. So what we saw here is that of these two transactions, only one got accepted by a client, the other didn't. And this is a core property of PBFT. So as soon as we have more than 3 times the number of faulty replicas, PBFT can guarantee that if two good replicas commit to some message, then they must commit to the same message. And to see why this is the case, say my first replica commits to a message 1. Of course, it only does it after receiving n-f prepare messages. So this green box is all these messages. Some of these messages can be from faulty replicas, so we take those out, but there is only f of those faulty messages. So then we end up with a set B1 of all the good replicas that sent me this prepare message. And we can do this for both replicas that committed to some value, and then we can see are those, is there an overlap between this B1 and the set B2? Because if they got different commit messages, if they committed something different, then they must have gotten different prepare messages. So they must have gotten them from different good replicas. And we see that as long as we have a lot of good replicas, more than 3 times the number of faulty replicas, then something just doesn't end up here, because the total number of replicas in B1 and B2 is, of course, 2 times n-2f, because they all need to be distinct. And if we want to guarantee that all of them are good, we must have that is less than n minus f. Then we can shift around some of these values, and then we end up with a conclusion that, okay, we must have started with only a few good replicas. So here we get a contradiction. So as soon as we have a lot of good replicas in comparison to the non-faulty replicas of the faulty replicas, we always have this guarantee that divergence just cannot happen. So if you look back, in this case, no matter what happens, the primary can do whatever it wants to do wrong, but either nothing gets executed or one thing gets executed and never two things. And that's good. So that's one of the things we don't need to take care of. But then the next step is, okay, if primary is faulty, how are we going to detect that and how are we going to deal with that? Because it might still end up not causing anything to get accepted. And to see that this is not that easy, look at a simple example. In this case, we say primary is faulty. It doesn't send anything to the third replica. So the third replica cannot contribute at all. Well, that's one way to see a fault. But the other thing that can happen, well, of course, that the third replica will at some point say, hey, the primary is faulty. I don't get anything. But another thing that can happen is that the third replica is faulty. It does get something from the primary, but it just ignores it. And then it just says at some point, hey guys, the primary is faulty, I didn't get anything. The problem between these two cases is that for all the other replicas, they are exactly identical. So if you look at replica 1 and 2, they get the same message from the primary, they get the same message from the third replica. So they cannot determine whether the primary is faulty or whether the third replica is faulty. So no matter how we're going to deal with faulty primary behavior, we also need to be able to deal with primary behavior that is somewhere between faulty that we can detect and that's faulty but we cannot detect. So this complicates stuff a bit. So let us first look at the case where the primary is so bad that we can detect it. How can we do that? Well, if the primary doesn't tag to anyone, then everyone can just say, okay, primary doesn't work for me. Everyone's gonna get a lot of votes for that. And if I get more than F votes, then I can say, okay, well, one of these votes must be from a good guy, so I believe him. Primary must be bad. So what are we gonna do then? We're gonna replace the primary, get a new primary. How do we do that? First, we choose the next primary. Usually, it's just the next replica. We just order them with some identifier or something like that. Then, of course, this next primary needs to start at a consistent state among all replicas. So it needs to recover the consistent state, because the current primary might have made a horrible mess. It does that by proposing a new view, and that's, of course, based on what everyone reports as the current state. And after that is valid, everyone switches to this new view, and the new primary can do normal DB15. So let's look at how such a view change happened. Well, we have a Byzantine faulty primary B that crashed a while ago. That's detected by a new primary P prime and by a replica L1 at some point. And they say, I want to change the view, the primary is faulty. Here is my list E of all the transactions that I have prepared, because we need to keep those. And of course, after that happens, the second replica, R2, gets two of these messages, and he can conclude, okay, one good replica said something is wrong, so I'm going to join in. And he also going to send a view change message due to that detection. Then the new view message of the new primary, P prime, at that point got three new view change messages, and it says, okay, based on these view change messages, I can construct a new view that is consistent, that contains everything that everyone ever prepared. And it does so by just picking n minus f view change messages, filling in the blanks that the old primary left, and proposing that. After that, everyone gets this new view message. They can check whether everything is valid in that message, move to the new view, and after that, all good replicas have a consistent state, and the new primary can start proposing stuff. Of course, a very important property in all of that is that if good replicas ever committed to a transaction in a previous view, then in the new view, this committed transaction must be maintained. To assure that, there's a very key property of DB15, namely, if you have a set of n minus 2f non-faulty replicas that committed to a message m, then in any other next view, that message is maintained. Why is that? Well, we just look at the new view message. That new view message contains n-f view changes. And then we can do a counting argument similar to what we already saw. We remove from these new view change messages all the messages from faulty replicas. We end up with n-2f view change messages of non-faulty replicas. And of course, the set B, if we compare that to the set F of all the people that committed, then as soon as we have a lot of non-faulty replicas, they must overlap. And if they don't overlap, we have a contradiction with the assumption that we had non-faulty replicas. So the view chains will always maintain things that gets committed. Of course, there are some technicalities that we skip over right now, but that's the basic of it. Looking back at that, well, we talked about how to deal with detectable failures, but there's a bit more to it. Because as we have seen, a primary can just ignore some replicas and that cannot be detected. So to deal with that, we can use checkpoints, and these checkpoints can be done by just all the good replicas that did finish rounds. To be able to deal with detectable failures, well, we've seen how we can replace one primary. But of course, the next primary might also be faulty and the next might be faulty. So we need, in the worst case, a real chain of F of these primary replacements. And of course, this harks back to the ETHEREUM consensus that already told us that we need at least F phases as a minimum. What we also need is, if you just look at the view change protocol that I described, that thing is super expensive because every view change contains all the transactions ever accepted. In practice, we're going to make that a bit more cheaper by just doing a view change since the last checkpoint. And the fourth thing we can look at is everything I told up to now assumes that the communication is at least reliable. If you don't have reliable communication, then a primary might seem to be faulty. And we can replace non-faulty primaries. And in the worst case, that can just continue until the end of days as long as communication remains unreliable. So we see that this view change process usually only converts to something workable if communication gets reliable enough. But well, also that is just a consequence of the limitations in practical systems. Any questions up till now? No? Okay, then let's continue. So we looked at the theory, we looked at practical consensus, but we have not yet answered the question, how are we going to get high performance? To be able to get high performance, we've identified two basic directions for improvement. And those are the directions we're looking at. Both of these look at, well, how do we provide high performance for data processing? And the key component there is just we need scalability. No matter what happens, if we need to find some way to add a resource in such a way that we're also adding performance. And if you look at a consensus system, of course, scalability is out of the question because in a consensus system, if we add resources by adding replicas or something like that, this means we kind of need more coordination to get all the replicas in sync, and that needs less performance. So it seems to be at odds, but there are still ways. So how do database systems, for example, get scalability? Well, one of the key techniques is, of course, to just do sharding. Instead of having a system that contains all the data, we can split it up into a system that holds some data and another system that holds the other data. For example, one system deals with European data, the other with American data. And we're going to need a little bit of coordinations between these systems to deal with a request with client transactions that deal with both of the data. But as long as most of the requests deal with only European data or only American data, this will add throughput by adding shards. And of course, we're also going to be able to add storage because, well, the shards only need to store some of the data. That's one of the key, one of the basic manners. Another manner is, say, instead of applying sharding, is we have the system, it does all updates, it does all read-only workloads. Well, we want to make it faster, so what can we do? Well, we split the system into a part that manages all the data, does all the updates, and we split off all the read-only workloads that are heavy and compute intensive into individual systems. For example, one that does analytics, one that does machine learning, one that does visualization. And if we do that, then we can even say, okay, this machine learning needs some specialized hardware to do TensorFlow. The visualization part needs some GPUs to be able to do that, so we can even specialize the system to improve performance even more. So in this case, we can get scalability by just adding specialized hardware, adding additional read-only workloads and additional systems. But of course, that's how a normal database-oriented system would do it. We are not that, we are a blockchain system. So how can we incorporate these ideas in a blockchain? Well, we only have one thing yet, and that's a consensus-based blockchain system. It's just a cluster that can manage data. That's our basic ingredient. Well, in a sharded system, we can say, okay, each of these shards could be such a blockchain. We can operate it independently, but then of course we also need something to allow communication between these shards. In a permissionless blockchains, we've seen techniques for that. We've seen blockchain relays, we've seen atomic swaps. But for our permission systems, we have to develop some techniques for that. Similarly, for role specialization, well, we can say that the central system that manages the data can be a blockchain again. And all these read-only workloads, well, people that want to do the read-only workloads can manage those themselves in any way they want. But to allow that, we need some efficient way for the blockchain to communicate all the updates to all these read-only systems. And in permissionless blockchains, we can see things like that in the form of light clients, but also here, for permission systems, we need some new technology. The key component here is that if you want to solve that, either reliable communication between blockchains or updates, we cannot really use consensus just because it's just too costly and too inefficient. It's the wrong tool. So the next question is that what new tools do we need and how are they going to work? But before that, maybe some questions from the audience, if there are any. Still none? Okay, then let's continue. So what new tools do we need? Well, we're gonna look at these two techniques that we just showed. So the first thing, for sharding, I already identified we're gonna need a way for permission blockchains to communicate between each other. And we formalized it within our group as the cluster sending problem. And the cluster sending problem, we can formalize it quite easily. We have two clusters. We want to send the cluster from one cluster to the other, a value. And we want to do that in such a way that the second cluster is going to receive that value. The first cluster wants to get some confirmation that the value was received. And very critical, because we're dealing with Byzantine behavior, the second cluster is only going to be able to receive a value if that first cluster agrees on sending that value. So the faulty replicas in the first cluster can do whatever they want, but they cannot convince the second cluster that some value was sent that was never intended to be sent. And this basically just boils down to the requirements for reliable communication between clusters with Byzantine replicas in them. Then the second question is, can we solve this problem? And it's quite easy. What we can do is just pick a lot of replicas in both of the cluster. If you pick enough replicas, then there must be good replicas in our choices. We just let all these replicas talk to each other. So at some point, good replicas will talk to each other and messages conveyed. The only problem is that this is, of course, a quadratic amount of communication and the number of faulty replicas in both of the clusters. And if you want a global scale sharded system, then we see that communication on a global scale is just very, very expensive. It's going to be orders of magnitude more expensive than within our cluster. So quadratic is maybe a bit too expensive. Then the next question is, can we do better? And to answer that, we have to look at some theory. And the first thing we can ask ourselves, is there a lower bound on the amount of communication that we need to do? And to illustrate that there is a lower bound, we're going to just have two clusters. One has 15 replicas, it's the top one. One has 5 replicas, it's the bottom one. And in both clusters, almost half of the replicas are faulty. And I'm gonna claim, in this case, that to reliably send something from the first cluster to the second cluster, we're gonna need 40 matches no matter what I do. To show this, I'm gonna show that with 30 matches, I'm always going to fail. So I'm gonna end up with a contradiction in that case. Of course, I want to minimize the whole faulty replicas in the first and in the second cluster. So I'm gonna try to spread out all the messages I'm gonna send. For the first 5 messages that I sent, I can just send them to each of the replicas in the second cluster. But for the second 5 messages, of course, because the second cluster is so small, some of the replicas in that second cluster will get several messages, no matter what I do. And the same also for the remaining 3 messages. Well, this is one way to send 30 messages. I can do it another way, but no matter how I do that, some replicas in the second cluster is going to get more messages than the other replicas. And we also know that 2 replicas in the second cluster can crash. So we're going to crash 2 of them, namely the 2 that got the most messages. And that already means that 6 messages that should have been sent got lost. Well, if we now count to see how many messages we have left, we see that only 7 replicas did send all the other messages. And in the first cluster, we know that there are 7 crashes possible. So we can just crash all of them. And then we see that if we just send 30 messages, then I can always find some way to crash replicas in both clusters to assure that nothing ever got sent. So we need at least 40. Of course, this is a very specific example. We can generalize this example a little bit. And in general, what we see is if you have 2 clusters, and the amount of messages that we need to send is proportional to the size of the biggest cluster. And below we have a more detailed representation if you want to deal with crash failures, and there we see that it's basically the ratio between the number of replicas in the smaller cluster and 2 and the number of faulty replicas in the bigger cluster. And of course we also have to deal with mismatches in the size of the cluster, so that's where these plus R and weird terms come from. That's nice. We've shown that there's a lower bound, and this lower bound is not quadratic. The next question is, can we achieve this lower bound? So can we do something that is that fast? The answer is quite simply yes. And we have a protocol here. I will not go into all detail, but the key component is that if you have a very big cluster that wants to send to a small cluster, what we do, we just, like in the example I gave, we divide up the big cluster in the replicas that are equal the number as the number in the small clusters, and each of these divisions just sends a message one-to-one to the smaller cluster. And if you have sufficient replicas that is more than the lower bound, then we know that one of the replicas will talk. One of the good replicas in each of the clusters will talk to each other, so they can exchange the value, and then the person in the second cluster can just broadcast that value. So I won't go all pseudocodes, but let's look at an example. So the big cluster is going to decide on the value. You can use consensus for that or something like that. Then it's going to send that value, and for that we're going to need global communication. It's expensive, but we minimize it. The lower bound in this particular example says that we have to send 6 messages. So we do that. We can also crash some people, and apparently we have 3 people that have crashed in the first cluster and 1 in the second cluster. Well, we do that. We erase all the messages that got sent between bad people, and we see that 1 message was indeed sent from a good replica to a good replica. The receiver says, okay, let's share this message internally. After that, everyone got the message. And that's basically the basic working of that optimal algorithm. We can then ask ourselves, well, we were still sending quite a lot of messages, and a number that's linear in the number on the size of the cluster. It's still quite a bit. So the question is, can we do better? And the pessimistic answer to that is no. We've shown that what we did is worst case optimal. Of course, we can also be a bit more optimistic and say, can we do better? Yes, we can. We can try to optimize for a case when things go correct. One way to do that is to use randomization. And if you do that, we can show that we can do it with only 4 messages, independent of the size of the clusters. Details for that are upcoming. They will be presented in a future paper. So that's all on the cluster summing problem. Any questions on that up to now? How are we on time?
I have about 5 minutes, I think.
Okay, then I'll have to rush in that, I guess. The second problem we looked at is how can we provide updates from a blockchain to read-only analytic systems, basically. And we call that the Byzantine learning problem. Slides not okay. The Byzantine learning problem, like I said, it's just we have a ledger, we want to share it to a blockchain, and we want to make sure that every learner that needs that ledger receives all of the transactions in the ledger, but not anything else. So faulty address can still not lie. And in practical requirements, we want to minimize communications, and we want to provide load balancing over, of course, all the replicas in our Byzantine cluster. And the key component in that is to just find a way to encode this ledger in a cost-efficient manner. To do that, we decided to run using information dispersal algorithms. And an information dispersal algorithm basically picks a very big value. It says we're going to break this up into n pieces, which we have n replicas, and each piece can be used to decode the original value. So if we get n minus f pieces, then we can already obtain the original value that we had. And we can, efficient information dispersal algorithms are so good that the number of pieces that we need to reconstruct has approximately the same size as the original value. So what we just do is assign every replica to one of these pieces. Every replica is going to broadcast one of these pieces. So every replica will then only do the amount of communication that's proportional to the number of good replicas. So in that way, we can solve Byzantine learning with scalability. Of course, we're going to need some details on how to deal with faulty replicas, but due to apparently we only have 5 minutes, we kind of skip over that a little bit. But so in practice, what we're going to do to assure that we're going to send big values, we're going to block up our ledger into a number of values that is proportional to the number of replicas. So in this case, 4. After 4 messages, each replica is going to encode these values into these 4 transactions into small pieces. I'm going to send that to the learner, and the learner, upon receiving 3 out of 4, can reconstruct the original value. And of course, after the next 4 transactions are decided upon, we can repeat that. Of course, we also, I skimmed over the details on how to deal with faulty replicas. They can send corrupted pieces or invalid pieces. And one way to deal with that is to use checksums. And to have checksums that are computationally cheap, we can use Merkle tree-based checksums. And for this, well, we just use standard Merkle trees. So let's skip over those details and due to time. And if we take all of that combined, we see that if we have sufficiently good replicas, then we can do this setup of a blockchain and learners that receive all the ledger in such a way that all the learners will learn this ledger. All the learners will only receive an amount of messages and whose size is proportional to the size of the ledger. So they won't get a lot of extraneous communication. We also see that the replicas that are sending messages each only send a proportional part. So if you have 50 replicas, then one replica will send 1/50 of the entire ledger. So in this sense, this problem we can actually, even in a consensus-based system, solve in a scalable manner. We can add replicas to the cluster, and that will reduce the amount of communication we need to do per replica. So that's good. Furthermore, if you look at the details of how we solve the Byzantine learning problem, you can also actually apply this to the design of the blockchain to ensure that the blockchain doesn't have to store a full copy of the ledger at every replica. So you can also use this to make storage a bit scalable within the blockchain, but of course this only works as long as the ledger is much bigger than the current state maintained at each of the replicas. So let us go back to the original problem. We want in our lab to reach high performance resilient data processing. We've looked at what practical systems already provide, what the theory says we can do. We have also identified in our work that if we want to reach this goal of permission net systems that are resilient, have super high performance, then we're going to need a very extensive toolbox to allow for sharding, to allow for read-only specialization, all that kind of stuff. And for that, there's quite a lot of work still left. But at the moment, we already have a small toolbox. So we have consensus, we have cross-blockchain communication, and now there's cluster sending and in permissionless systems, we have relays and atomic swaps. And we can enable some read-only participation, but we're going to need a bit more. But from our perspective, from what we see is that this high performance resilient data processing, we can reach that actually. And quite soon we will actually be able to show some practical systems that really are scalable. It's still ongoing work. We already have some published results on all of this work that can be found on our websites or at all these venues. Pretty soon we'll probably also have some work on really having sharding built on these primitives, so that's also exciting. And as far as I know, in the next session, my colleagues will talk a little bit more on not the high-level approaches that we want to achieve to reach a high-performance system, but they're going to talk about the system perspective, about consensus protocols, and about the nitty-gritty of implementing those to assure that each permission blockchain is, of course, as fast as possible. That's all for me right now. So if there's any questions or any remarks, then well, we have time to answer them.
Okay, so thank you very much for this first part. We have a question from Kaiwen saying on where does sharding fit in your picture? Is it included in cross-chain communication?
So let's go back. Oh wait, that's too far. So if we look at, where is the picture? Ah, there it is. So sharding is basically a high-level system design, right? So in the picture, what we're going to see is that this European cluster, that's a permission blockchain. This American cluster, that's a permission blockchain. But of course, we can quite easily design the system so that they can deal with European requests, American requests. But if you want to do more, if you want a request that transfers, for example, money from Europe to America, then we need to do a lot more. We need some sharding protocol to coordinate between these two things. And the most basic component of such a sharding protocol is just the ability to coordinate between these replicas. So what we envision is to first provide the basic primitives to allow communication between these shards. Then on top of that, we're gonna see how we can translate normal sharding protocols to also work in the setting of Byzantine behavior. But like I said, we already have this basic cluster sending primitive. The sharding is work we're currently in the process of finalizing.
So you have one more question. So Kaiwen, so the cluster sending, the basic idea is to reduce the number of messages. How do you reliably communicate between two clusters, two Byzantine clusters? Now they could be different shards, they could be fully replicated, but what is the that construct, the primitive? And well, if it is geographically separated, well, if you minimize that the cost of that communication, well, you even save more. But the basic of it is, what is the minimum number of messages to require to reliably communicate between two clusters without running consensus? You can always solve it by consensus, which is expensive. And the cluster sending gives you primitive, and it gives you a lower bound on the message complexity.
Okay, thanks. Because I was asking because the sharding solutions we see in blockchain are proposed that they usually rely on a random function to assign the validators to the different shards or the clusters, as you call it here, because of security reason, right? To avoid collusion and things like that. So you're proposing an alternative approach that's not random, but it's based on geographical location. Is that correct?
At the moment, we're looking at several options, but indeed, there have been some practical systems. Some do some type of global consensus. Others say, well, for cross-shard transactions, we're going to just assign some set of replicas to decide everything that's cross-shard. But of course, all of these approaches are not very decentralized, so you're not going to get the maximum benefit of sharding. So what we are looking at is how can we do it in a much more decentralized way. And as far as we can see, it is possible. We already have some results on that. The other options would indeed be using committees that are based on some random function.
Right.
But I don't really believe in that, because if you're going to assign a committee, that committee is fixed. It's still some form of centralization in that design, so it's going to limit something, right?
Yes, but usually the committees are shuffled at some interval of time
but still, that means that in the interval of time where we have the single committee, at that point, that committee is the bottleneck if you're going to have a lot of cross-shard transactions. So even if you have like 15 shards, and we have transactions for the first 2 shards, the second 2 shards, the third 2 shards, that should just be scalable, right? That shouldn't be bottlenecked by some committee. But like I said, there are options to not do it in that way, and we hope to be able to publish it soon. So.
And again, so Carmen, just to stress on that, in addition to what Jelle said, the cluster sending is a much more basic primitive. Is that you want to send a message between 2 clusters. These 2 clusters could be shards or just be 2 clusters of 2 different blockchains. Doesn't really matter what those 2 clusters is. But the key is that these clusters are potentially Byzantine. And how do I reliably send one message from one cluster to another? And that's a basic primitive. So you can now build a variety of sharding protocols. So we're looking at about over 20 different sharding protocols we're actually looking at. And all of these, the basic construct of communication is this cluster sending in order to show the optimality on it. So it's a primitive. It can even use in geo-scale consensus on a fully replicated system. Doesn't have to be partially replicated as in the sharding case. It's just about how do you do reliable communicate.
I see. Okay, thanks. So tell me
Yeah. So I just wanted to say, so basically we're in the lunch break now. So depending on your time zone, it's either lunch or late breakfast or dinner. And so this will be a break until 7 p.m. Central European time, or let me check again. So I checked it earlier, but I forgot again.
10 a.m. Eastern.
10 a.m.
No. 10 a.m. it would be a Pacific time.
No, 1 p.m. 1 p.m. Eastern.
1 p.m.
Yes.
1 p.m. Eastern. Yeah. So approximately 1 hour.
Okay. 1 hour. Okay. Final remark from me for everyone that's interested in this work. We're gonna post our slides on these websites. My slides also contain a very long section on references where most of the results that I spoke about are presented. Also some other perspectives on blockchains, on permission blockchains and that kind of stuff. So if you are interested, take a look at that. Have a great lunch, everyone.
So see you all in 1 hour. About 1 hour. All right, thank you.
Thanks.
You are here. We are going to start the second session of our tutorial. In the previous session, Suyash gave a brief introduction on the blockchain. Jelle talked about the high level and theory aspects of blockchain. Now in this session, we are going to dive deep into modern Byzantine fault tolerance protocols and take a high-level look at them, compare their workflow, their communication complexity, and how they manage faulty cases. And after that, we are going to represent three works of ours. So they are also a modern BFT protocol. And at the end, we are going to have a hands-on tutorial on the resilient DB, the blockchain platform, the permission blockchain platform that we have developed. And yeah, that's it. So as Jelle talked about the PBFT, I'm not going to go over it, but just for a brief review, PBFT was the first Byzantine fault tolerant protocol. It had three phases. Two phases have quadratic communication complexity. It provides safety and liveness in a period of partial synchrony. And it has a view change subprotocol for replacing malicious primary. So the workflow of PBFT, just to remind you, the client sends its request to the primary batches the request and send to the nodes as a pre-prepare message, which is a round of O of n communication. The next round would be prepare, a quadratic round of communication. Everybody will send everybody that I have received message from the primary. And the end, at the end, the last round is a commit round, which is again quadratic communication complexity round. And after the commit round, everybody will execute and send the reply back to the primary. The the view change subprotocol also Jelle showed. I'm just going through the workflow. After finding out that the primary is malicious, everybody will send view change message to everybody, a round of quadratic communication that everybody will send their states to the new primary, and everybody will acknowledge the new primary. Once a new primary find out that everybody has received enough view change message, it will create a new view message containing the information for the replicas to keep them up to date to the new view, and then entering new view and starting accepting client requests. Up to now, we talked about PBFT. After PBFT, there was a paper on SASP 07, which called Ziziva. It was trying to reduce the phases of PBFT and also reducing the message complexity of practical Byzantine fault tolerant protocol by employing the speculation to achieve a consensus in a single phase. Ziziva has the best performance in the actually optimal performance in case of no failure. It has just one phase and in a linear communication complexity, but it depends on good clients. It assumes that the clients should not be faulty, and the clients also are part of the consensus. It needs, for a fault-free case, it needs 3f+1 identical response of speculative execution. But in case of only one crash, it needs to wait for a specific, the client needs to wait for a specific amount of time to proceed, and that makes Ziziva severely poor perform in the case of even just one crash fault. And this is also counterintuitive to the fact that the BFT protocols are going to tolerate faults. And recently, it is proven that's unsafe, and there could be some cases that Ziziva might not keep the replicated state machine same in all replicated nodes. However, Ziziva has made a lot of contribution for the BFT protocols because of its nature of single phase and being linear. So in this slide, we're going to go through the high-level overflow of Ziziva. As of PBFT, the client sends its request to the primary. Primary will send a pre-prepare message to everyone. At this point, everybody will speculatively execute the transaction and send the response back to the client. In the fault free case, everybody 3f+1 node will execute the transaction speculatively, and they will, because of the deterministic execution, they will have identical response, and client will get 3f+1 identical response, and it can proceed to the next request, and the consensus is done in just one round of linear communication. It seems so perfect, everything is good, everything would perform well. But what happens if there's a Byzantine replica, or even there's a crashed replica? In this case, the workflow of Ziziva will change a bit, and it will add one more phase to let everybody know that the transaction has been committed, and that would be responsibility of the client. Just like normal phase, the client will send request T to the primary. Primary will batch the request and sends a pre-prepare message, assigns the sequence number, and sends a pre-prepare message to everybody. Everybody will execute and send reply back to the client. But here, one replica is not able to do that because of acting Byzantine or being crashed. So at this point, the client will needs to wait for 3f+1. This is where the timeout happens, because the client doesn't know that the message of the Byzantine replica is arriving late, or it is crashed or something. So it needs to wait for a specific timeout before proceeding. That timeout and that wait will severely degrade the Ziziva's performance. After this timeout, the client will create a commit certificate. If it receives at least 2f+1 identical response, it will create a commit certificate and will send that commit certificate to everybody, so everybody will understand that 2f+1 node has executed this request, and once 2f+1 replica has executed the transaction, we can assume that the majority of the non-faulty nodes has executed the transaction. And after this round, the consensus is done. And as you can see, it has one more round of linear communication, but the timeout at that brown circle will degrade the performance of Ziziva. In this presentation, I'm not going to cover what happens if the clients receive less than 2f+1. That's where view change happens for Ziziva, and recently it's been shown that for a consecutive view change, there could be cases that primary of new view cannot keep up with all the information that has been committed in the previous view. So PBFT and Ziziva both tried to make BFT protocols fast. However, Eve came and introduced the execute verify architecture instead of order execute. In Ziziva and PBFT, all transactions are ordered, and after getting ordered, then they will execute and send the replies back to the primary. However, Eve changed that architecture and tried to exploit the advantage of parallel hardware to improve the performance. Eve is designed to for workloads with transactions that are computation intensive to execute. and it executes multiple requests concurrently when it's received the request, and after that tries to reach consensus and agree on the output. So the Byzantine agreement is an output instead of sequence number, which was in PBFT and Ziziva. It allows divergence. It means the nodes can reach to different states, but it allows rollback if it's necessary because of the supporting non-deterministic multi-threaded execution of the transaction. So it focused on the things that neither Ziziva nor PBFT focused on, which is exploiting the parallel hardware to increase the performance of consensus. So this would be the workflow of Eve. I think the animation is wrong there, but yeah, that's the problem. As of PBFT or Ziziva, the client sends their request to the primary. Primary batches the client's request and make a batch of requests and sends as a pre-prepared message to everybody. At this point on the brown circle, everybody will execute all the batches speculatively and creates the execute token, which are the output of execution that the consensus needs to be done on top of them. So after they execute their transaction, they will transfer execute token, which are the output of the execution. And after that, we have 2 rounds of PBFT, prepare and commit or rollback rounds, which are quadratic. And as you can see, it is communication intensive and it hasn't reduced any communication or any phases in compared to the PBFT, but it has its own advantages. So after sending an execution token, they will everybody will send a prepare message on top of those execution tokens to let everybody knows that they have those, and at the end of a commit round, they can reply back to the client and say, yeah, the consensus is done. We have executed all those transactions, and you are good to go. So if so there's a question here. In what situation? I will read the question for you. In what situation will there be a rollback? The order of execution cannot be determined during the batching. Yes, the order for the first question, when the rollback happened, because of this multi-threaded execution, Eve claimed that these results can be different because it can happen for a multi-threaded execution to produce different responses because of the non-determinism. In that case, if when they are sending execution token after sending prepare message on those things, if there are conflict, then instead of commit there would be rollback. If they have enough identical execution token, there will be commit, otherwise there would be rollback. The order of execution cannot be determined during the execution. Yes, it can, but they haven't done that. They want to execute all those transactions in parallel. So once they have a lot of transactions in batch, they do not have a specific order for them. So they have the order for each batch, but the order of each transaction in batch is not determined. So they can execute them completely, concurrently and in advance. Yeah. Thank you for the question. So after the last phase, which is commit or rollback, there would be reply back to the client, and the if will be done. So recently there's a protocol called Hot Stuff BFT Consensus of the Lens of Blockchain, which published in Part C 2019. It was a huge advance in the BFT protocols. The Hot Stuff has made BFT protocol completely linear and in a safe way, as opposed to Ziziva. The basic version of Hot Stuff is so simple. As you remember, in PBFT we have 3 rounds, 2 rounds of quadratic communication. Hot Stuff splits each of those quadratic communication phases into 2 linear phases, exploiting the threshold signature, and with 6 rounds of linear communication, it reaches consensus in a fast way. It changes the primary or the leader in every round, so it distributes the burden of being primary on all nodes, and also it also advantage from the having multiple primary in each round of consensus, so they can run in parallel. And yeah, it is one of the recent BFT protocols, which I think the Facebook's Libra is based on chain Hot Stuff, the second version of Hot Stuff. It has 2 versions. The basic one is just unfolding the phases of PBFT in 2 rounds and make it linear, but the chain Hot Stuff will use the pipeline version, and by unfolding the PBFT rounds, it will make a 6th round, but by chaining those rounds to each other and pipelining every request, every part of consensus to the previous consensus, it will make it so fast and perform better. So we will go through the basic version of it, just to see how is the workflow of Hot Stuff and how it will use as a threshold signature to unfold the quadratic phases of PBFT. As like every other BFT protocol, client send request to the primary before starting the new view. In each round of consensus, everybody will send view change message to the new primary, and after new primary will receive enough view change message, it will send a proposal which consists of a sequence number and also client transaction, which is identical to the prepare message in PBFT. And at this point, everybody will send a prepare vote to the primary. When primary receive 12+1 prepare vote with partial signature, it will create a threshold signature using those partially signed messages from prepare vote of everybody else, and create a whole signature and distribute it back to all other nodes as a pre-commit message. Once everybody receive a pre-commit message, they will send a commit vote to the primary. And again, at this point, primary will create threshold signatures using the partially signed messages from the pre-commit votes and distribute it to all other nodes as a commit message. At this step, once all nodes receive a commit message from the primary, they can understand that the transaction has been committed, and they can send back and they can send a commit vote to the primary to show that yeah, we acknowledge that we received the commit. And at this point, the primary can send a decide message and tell everybody, now you can execute your transaction, and proceed to sending next view change message to the next primary. As you can see, these large lines on the bottom. These are the 3 phases of PBFT. Each has been splitted to the 2 rounds of linear communication using a threshold signature. Once the primary receives those votes, it will create a threshold signature, and these threshold signatures are not heavy as commit certificates, but yes, that was hot stuff, one of the most recent BFT protocols. I think from here, Suyash will present proof of execution, which is one of the artworks. Let me stop.
Thanks, Jelle.
Yes.
Also, maybe we can pause, see if there are any questions from the audience.
Yeah, perfect. Yeah, sorry. If there's any question about Eve, Ziziva, or hot stuff, you're more than welcome. So I can stop.
Maybe I can say something here. So in hot stuff, because everything is coordinated with the primary, and there's no quadratic communication, like, would you say it's more susceptible to a single point of failure on the primary side, or it has the same security property?
In general, it has the same.
It has the same safety properties, because hot stuff is using different leader in each round of consensus. So if one round of consensus, the primary is malicious, so they do not need to do a heavy rounds of view change message like PBFT or Ziziva, and the next round would be completely independent from the previous round, and it's not that much susceptible, but it's susceptible to the primary failures, but the safety and recovery protocol provide the full proof of safety, which are not in the context of this presentation to get more in details of how they prove safety in case of primary failure, but they provide complete and full proof of safety in the case of primary failures.
Okay. And then other than that, in the chain hot stuff variant, is there also some support for rollbacking? Because I suppose you don't know the result of the execution of the previous round before you start the next round?
Yeah, you don't know the results of execution. The execution will not happen until the commit phase, because it's order execute architecture. So it needs for every node to get commit message and receive commit message and understand that 2f plus 1 node had received the commit stage to execute the transaction. So there would be no rollback. Yeah, there would be problem if some of the transaction will not receive enough prepare vote or commit vote, but that would be another issue, not rollback. Rollback just happens when the execution happens, and in hot stuff there would be no execution before complete order.
Okay, I see. So you're saying all the results of the execution is done afterwards?
After, yes, after
okay.
Commit phase.
Okay, perfect. Okay, thanks.
So, sorry, I just have more of a practical question, which is in terms of requirements for businesses, how many actually need BFT and how many say it's okay, we don't?
You mean
do you have a general idea in terms of
applications of BFT protocols?
Like using BFT for blockchain in general?
For permission? Yeah.
Let me answer this question. It's a very interesting question, but I think blockchain as such requires BFT by itself, because I mean, there have been blockchain models just like one suggested by Hyperledger, where they say you can use a Kafka with it, but I mean, it makes no sense to have blockchain without BFTness. I mean, it already means that there has to be some sort of security, and there needs to be a Byzantine fault tolerant protocol to running. If we remove BFT itself, then it's not exactly blockchain. That's it.
Okay.
And as for, yeah, please go ahead.
Okay, yeah, that's what I was wondering. So I was curious to know because, right, I mean, the high cost of having, 3 phases of communication and high client latencies and all that, I mean, is it something you can do without in certain contexts or not?
Perfect. So now again, the question is, do every protocol have three phases of latency, right? PBFT was the one which actually proposed the idea of having 3 phases of latency, and it said that it has to happen. But I mean, since PBFT, there have been many protocols, and like, for example, Hotstuff is one of the protocols in this direction, which says that, hey, we don't need 3 phases. We can do things linearly, and it is possible. We don't even need view chain. That is what Hotstuff's whole direction is. And then now, after this, we'll present some protocols. Yes, I mean, obviously, compared to Paxos style protocols, BFT style protocols are costly, but I think it again depends on what applications are we looking at. And if the application, any application which is assuming there will be malicious adversary who's going to attack the system, we can't rely on a CFT system or a Paxos style system.
And also, it's going to add on that is that we also kind of experimentally we see in that Suyash is going to talk about. You can scale to 91 replica and still have anywhere between 50,000 to 100,000 transactions per second. Sure, I think traditional databases can definitely can do more than that, but with 91 copies of the data, 91 replicas, still achieving thousands of transactions per second, I think it will satisfy probably a large space of application. Not all of them, but probably a large.
Okay, thanks.
Perfect. So yeah, again, while I'm presenting, please feel free to ask any questions. You can directly shout out, that's fine. Otherwise, you want to just write, just feel free. So now that Sajjad has given us a nice summary of existing protocols, what we'll be looking next is different type of protocols that we have tried to design in this space. And when we started working in, we have been working on this for past couple of years, and we started working, we looked at PBFT as a start point, and we saw like, hey, what are the different dimensions we can actually move, and what are the existing protocols, what are the limitations? So first we saw PBFT, and it has 3 phases of communication, and we saw there are 2 phases which require quadratic communication, something which Kwazaima just said that it is something expensive, and we all agree and everyone agrees. And that's why, so since PBFT, there have been many more protocols. Ziziwa was one protocol which said that, hey, we can do things linearly, it just requires 1 phase. But Ziziwa, it depends on client, it cannot handle any failure. And recently, it has been shown that Ziziwa is actually unsafe. But then there have been some protocols like Hotstuff, which shows that, okay, things can be safe, we can still do linear, but Hotstuff requires high latency because there are many phases, and it is also sequential. Then in another direction, there were some protocols that said, what if we move beyond 3f+1 replicas? Because all the BFT protocols say we need 3f+1 replicas. What if we have 5f+1 replicas? Can we do faster? And then there are protocols like QU or HQ, which basically say you can do that. But clearly, we don't want so many replicas because 3f+1 replicas already mean much, and then it's a larger. Then there's another space which says that, what about I have something called a trusted component? Like these days we are seeing rise of Intel SGX and other components, right? And can we use these components to gain more throughput, or can we actually reduce the requirement of having 3f+1? And then there is a trusted component space. But again, trusted component means that there is a component, your system is completely dependent on that component's security. If that component dies, everything dies. So I mean, so there is whole space, and a lot of these requirements are there in existing protocols. What we try now is that, can we design protocols which are bereft of these existing dependencies and which can still outperform? And in this presentation now, we'll see 3 different dimensions. First, we'll try to see, can we actually reduce some phase? Then we'll try to see, can we actually scale out? And then we'll try to scale up. So 3 different protocols which will try to do these things. The first in this direction is basically what we call as proof of execution protocol. And this protocol, it is visible on archives if you want to go ahead and look whenever you want. The key idea of this paper is that we still allow replicas to do speculative execution, But what we do is that we promote 3 linear phases, and we require no dependence on client, no need of any special cryptographic primitives. We don't require any trusted component. And moreover, one thing which we allow in this design of proof of execution is basically say that in this presentation right now, I'll show a design with threshold signatures, but our protocol can also be used with MACs, missing authentication codes. You can use that. So if you want to use something which are less costly primitives, go for MAC. If you're fine with costly primitives, then you can go with threshold signatures. And moreover, Ziziva says like, hey, there's a fast path, or if everything is good, there's nothing bad, then let's go ahead and do it in one phase. But if even just one replica fails, then client has to wait, and that whole value depends on the timeout. And then when the timeout actually happens, then a next phase starts. So there are a lot of these twin path protocol. There was another famous twin path protocol, SBFT, which came in 2019 in DSN. So that these twin path protocols require a wait on the timeout. In proof of execution, we don't require any twin path. We don't require dependence on client. We don't require any cryptographic expensive primitives. How do we do that? First, this is a very simple table to show the cost. As you can see, PoE performs quite better compared to state of the art. Now let's see how PoE works. Well, here a client sends a request to the primary, and we have 4 replicas. We are assuming a system of 3f plus 1, f is equal to 1. And there's one Byzantine replica. We'll assume the Byzantine guy does not reply. Now, when primary gets this client request, he will send everyone the pre-prepare message. Well, this same exactly what is happening in PBFT. But now things will start changing. These 2 replicas will now create a sort of a signature share, okay? And they will send the share to the primary. So in threshold signatures, the whole idea is that if there are n participants, and out of these n participants, you can get k shares, then you can combine these k shares to create a complete threshold signature. And the signature can act as a proof that there were actually k participants who participated in creating this share. So that is what happens, right? In this case, we are assuming in PoE that we need 2f plus 1, k is equal to 2f plus 1. So if out of 3f plus 1, primary receives support from 2f plus 1 people, he receives shares from 2f plus 1 people, then he can create a complete signature, and he can send that signature to now everyone. So that is what is happening at this point in time. Primary received shares from other replicas, and then he creates a share at this point in time, and he sends to all the other replicas. What happens at this stage is interesting. When these replicas receive the share from the primary, at this point in time, these replicas got a partial guarantee. They know that, hey, we got some requests from the primary. Primary was saying, let's start doing T. And now we have a share which talks about that at least 2f plus 1 people got this information about T. So these replicas perform the speculative execution. They speculatively execute the transaction. They reply to the client. Now, how is this protocol different from PBFT, apart from number of phases? First, there is no quadratic communication, A. Second, if you see, the replicas are not waiting for complete guarantee. They are only waiting for a partial guarantee. Each replica, whoever got this full signature, at this point in time has an idea that there were majority of people who knew about this thing. Now, with that much guarantee, this replica can go ahead and execute. But in PoE, the client requires a little bit more information than other protocols. The client needs to wait for 2f plus 1 responses. In PBFT, it was f plus 1. In ZZY, it was 3f plus 1. So we lie somewhere in the middle. Our client requires 2f plus 1 responses. And when client gets 2f plus 1 identical responses, he is ready to mark his request complete. Now, if the primary is bad, then this guy may not send to everyone. He might send to some people. He might send distinct requests to different people. In that case, client may not get 2f plus 1 responses. And in such case, PoE needs to basically initiate the view change, basically initiate the process of replacing the primary. Now, when the primary is getting replaced during this whole process, it is possible that one replica, so it is possible that this primary was bad and he sort of gave a wrong transaction or different transaction to this person. He said to these two people, hey, let's do transaction T1. And he told this person, let's do transaction T2. And this guy somehow got a share and he was ready and he executed the transaction. Then this guy needs to basically roll back. So POE allows a notion of rollback. It says that, hey, if you are not in a consistent state in comparison to other replicas, then you need to roll back. But there's a catch. POE never rolls back the transaction if the transaction has been marked complete by the client. Why? If a client got 2F+1 responses, if a client got support from 2F+1 people saying that, hey, the request is complete, that request will never be rolled back because there are already majority of people. Because in a system, there can be only F bad people. And our client got response from 2F+1 people. So there are F+1 good people who are saying, hey, we saw this request and we have executed. So that request will persist in time. And that's why whenever a client sees the request is complete, that request is never rolled back in POE. Now let's go back to the view chain protocol. So if this primary was bad, then everyone will detect same like PBFT and they'll send a message to everyone that, hey, let's remove this primary. And then the new primary, there are some more replicas. So initially these two replicas detected first. Now next, finally this replica also detected. And when the new primary gets messages from 2F+1 people, it starts the process of throwing out the new existing primary, and it starts the new state by sending everyone the new view message. So this is the whole view chain protocol. And the view chain protocol of POE is not quite different from PBFT, but it provides some interesting guarantees like rollbacking the state, and that the client, if the client has marked a request complete, then that request will persist. So let us see how does POE perform in comparison to other protocols. We thought of doing some experiments, and as Mo was saying, one of our whole point was to see, can we actually scale POE to larger setups? I mean, a lot of papers scale with 4, 16, 30 replicas. We thought of going up to 91 replicas and see how does POE perform. And it is clearly visible, as you can see, POE performs better than every protocol. Now, interesting question here is, why is this hot stuff and ZZWeb perform low? So ZZWeb performs low because a single failure makes its client to wait indefinitely. And that just reduces throughput. It just goes bonkers. And why does hot stuff perform so low? Well, even though hot stuff uses its chained version, and its chained version will say that, hey, everyone just needs to wait for one message. And even though hot stuff allows changing of primary. But if you'll see beneath the skin, it's still sequential. Why? Now let's assume a system of n replicas and n is equal to 4. The first primary will start consensus. And then the second one can only start if the first is finished. While POE and PBFT type protocols, they have an opportunity of sending a lot of requests. And that's why POE outperforms other protocols. And similarly, if you can see, POE attains quite low latency compared to other protocols. So this is where I conclude POE. But before I move forward and start next protocol, if there's any other question regarding POE, I think this is a good time for someone to ask. Okay, I'll assume there's no question, or I don't know. I think I'm not able to see questions if there are questions. Yes, yeah. Okay, so next we thought of, next our idea was, okay, we have reduced one phase of PBFT. We are able to linearize the consensus. What can we do more? Can we basically parallelize it? Can we actually, why is the whole protocol dependent on one primary? Why is the one primary the person like who has to do everything? Why do all the replicas just need to wait for this guy to dictate everything? And that is the whole purpose of our next design. Basically, we want to scale. We have seen there were a lot of blockchain databases which have been using PBFT in their design. And traditional databases allow a lot of primaries. Traditional databases basically say that, hey, if you get a request, do a consensus, it's a Paxos style consensus, and just commit the request. And in these BFT protocols that we have seen, they're all designed with just one primary leading and everyone following what they're doing. So that is the aim of this protocol. The next protocol which we're going to discuss, we are saying that we don't need one primary. Everyone can become primary. And isn't that the true nature of blockchain? Basically give everyone the same power. And what's the advantage? That basically now there will not be just one malicious guy who can actually change the system. There are other people who are looking at the system also. They're also running the transactions. And in the previous, if there was a malicious primary, then you have to replace the primary. And while the primary is getting replaced, everything has to be shut down for primary to be removed. In this case, we can do things better because there are other replicas who might be acting as primaries and who are actually good because they're only F bad people, and they can actually continue to let the system proceed. So how do we do that? We present this algorithm which we call as MBFT, which we call as multi-BFT, multiple presenting fault tolerance. And what do we do is that we assume this protocol has 3 stages. In the first stage, we run Z parallel instances. For the sake of this presentation, I'll assume we'll work with PBFT, but multi-BFT is a paradigm and it can work with many distinct protocols. So how do we do that? First, we have these N replicas. We'll ask all of these N replicas to run Z parallel instances of PBFT. Good. Each instance will have its own primary. We'll ensure that each primary is being run by a distinct replica. All of these instances will perform consensus on their requests. So let's assume we have a nice case where we have 4 replicas and we have 4 instances, each replica is running 4 instances, and then everyone is running their own consensus. Once everyone does consensus, we'll somehow create a global order of this request. And finally, every replica will execute these requests in order and reply to the client. Let's look at a very simple example. In this example, which we have a scenario where we have 2 clients and we have 4 replicas. This is replica 1, replica 2, replica 3, replica 4. And we'll assume a very simple case. We'll assume there are only 2 instances. So every replica has 2 instances running parallel. Now, how does this happen? First, we'll say that each client will send request to its own primary. Let's assume we have a mapping where clients will know which their primaries are, and every client sends a request to their primary. Now, when that happens, each primary, if you'll see, will only send messages to its own instances. So this guy sends to his own instance and this guy sends to his own instances. Now, each instance is now performed the next stage of PBFT. This is the first stage of PBFT, pre-prepare, where primary sends message to all their own instances. And then each instance performs the prepare stage. Then finally, each instance performs its commit stage. And now things become interesting because at this point in time, if you see at every replica, if everything goes fine, they have both the request and they have information that both the requests have got committed. Now they will somehow order these requests and then they will reply to the client. So one of the most interesting part here is how do we order this request? In a simplest scenario, the ordering is very easy. Let's assume we give every replica an identifier. Let's call this as replica 0, 1, 2, and 3. Now 0 is the primary in this case and 2 is the primary in this case. So we can have a very simple scheme that whoever has the smallest identifier, his requests get executed first, or the other way around. Obviously, this scheme may not be very secure. So we have other options also that we can say that, hey, how about we hash the request, and because the hash cannot be identified till the end of the whole process, and then we actually execute the request based on the hash. So there are a lot of details about how do we actually order security, and I'll ask everyone, if you're interested, please go ahead and look at the archive version of the paper. And now once everyone has order the request and they've executed, now they reply to the client. But obviously, we have a system where we are allowing multiple people to act primary. Until now, we had protocols which were very nice because there was only one bad guy and you can just say, hey, this is the bad guy, let's throw him away. But now in this case, there can be many bad guys. And let's assume our Z is equal to just F plus 1. Then you can have up to F bad people and there's only one good person. So what can these bad people do? Well, these bad people can sort of collude and they can ensure that the whole system stalls. For example, I'll give a very simple example. Let's assume we have total 2F plus 1 good people, and let's divide these 2F plus 1 people into 3 sets. There's a set of A replicas, set of B replicas, set of C replicas. And these are the remaining F bad people. Now, these F bad people, and let's assume we have somehow 3 primaries, and of the 2 primaries, P1 and P2 are the bad primaries, malicious people. Now, P1 can send this request to A and C, and P2 can send this request to only B and C. Note that B didn't get this request, OP1, and A didn't get this request, OP2. So from A's perspective, the only request which has committed is this one, OP1, and from B's perspective, it's only OP2. Clearly, A cannot execute the transaction because it needs 2 requests from this round. And similarly, B is also stuck. So 2F replicas are just stuck. The only person who could do the request was C, which is just 1 replica. And if you'll see there are F clients, F bad people. So client will get F plus 1 response. The client will go home, he'll be happy. But the system has 2F bad people who are just stuck. The system cannot make any progress. How do we handle this case? Well, we allow a solution optimistic recovery. We basically make our replicas detect these cases. And when replicas of multi-BFT detect such cases, now they'll basically send us lightweight checkpoint protocol. Basically, they'll make everyone send messages to each other that will help them recover. So we thought of doing scalability test, and these and for scalability, we thought like, okay, let's just try to make 2 variations. So in the presentation, we were just talking about PBFT version of multi-BFT. We thought of even saying, can we do even a C0 version of multi-BFT? And as you can see, the multi-BFT versions outperform almost all the other protocols. And why do we get this perform? Because these protocols are running multiple instances. And note that we're only running F plus 1 instances at this point in time. It's possible that for some setups, if you run all N instances, then the performance might even go higher. Okay, so here I conclude multi-BFT, and after this, we'll start next protocol. So if anyone has any questions, then please let me know. And yeah. And Sajjad will continue the rest.
Thank you, Suyash, for TBFT. And up to now, we presented 2 other our protocol, PoE and multi-BFT, and also a lot of some of the modern BFT protocols that are existing. Each of them focusing on a specific problem, for example, parallelism, exploiting the parallel hardware, or I don't know, reducing the phases. But there's a problem that none of these protocols took a look at, and that's a global scale blockchain protocol. As you all know, the purpose of blockchain is decentralization, and replicas should be far apart in a geographic distance, and mostly when people are experimenting their protocol, they usually do not use the geoscale machines and put nodes geographically in a distant places. And the geoscale resilient blockchain fabric has come to overcome this problem. This paper has been published in Proceeding of VLDB 2020, and we will be also presenting this work in the VLDB 20. So here is the vision of geoscale Byzantine fault tolerance protocol. And as you can see, we cluster nodes of our system into different regions. For example, as you can see in the left side, we have clustered nodes in America in one cluster, nodes in Africa in one cluster, nodes in Asia in one cluster, and also nodes in Australia in one cluster. We will be going through the protocol and how it's worked, but at high level, as you can see, each region is responsible to handle its own client request and transferring the proposed block and committed block in each cluster to the other cluster with other clusters with minimal intercluster communication to achieve to reduce the geo-scale communication, to reduce the intercluster communication to achieve high performance. And as you can see, these B1 and B2 are transactions of different cluster which are being transferred. Those blocks are being transferred between the cluster with a minimal communication. So GeoBFT is a topology-aware protocol which, as I said, groups replica into cluster, and each of those clusters are responsible to handle their own transactions and transfer and their results to the other cluster. It has three phases, three main phases actually, which is the first one is local replication. Each cluster will be replicating and doing consensus on its own requests, and after that we need an intercluster sharing, which sending those results of those consensus instance, or in the blockchain terms, transferring and sharing those blocks to the other cluster. And at the end, they will be order and execute all those transactions in a deterministic order. We assume that there will be at most a faulty node in each cluster. So if we have three clusters, we will have three 3f+1 nodes, and we tolerate up to f faulty node in each cluster. So the workflow of GeoBFT is as this figure. We have two clusters, cluster 1 which is C1 and cluster 2 which is C2. Each of them have their own clients and their own primary, and each client will send their request to their primary. The primary will do the local PBFT consensus on their transaction, which is completely PBFT, a round of prepare and commit. And as you can see, the communication in these different regions are completely local and so cheap in compared to sending message from, for example, primary from the first cluster to the other cluster. And after doing a local replication or local PBFT on each request, they will share their results or the certificate of commit of that transaction in their own cluster to the other cluster. If we had three clusters here, each cluster will send those commit certificate to all other clusters. And this sharing consists of the block, the actual request of clients, and also 2f+1 signatures of proof of commit of the local consensus. So once a node in the cluster 2 receive the commit certificate from cluster 1, it can unilaterally understand that there has been a consensus on this request on the cluster C1, and majority of correct node in that cluster has been. If I think we have a question here. So actually, so the question is, does it only share with the subset of replicas in the other cluster as shown here, or will be or with all? If exactly in one more click of this figure, there would be local sharing of those commit certificates. Once a node receive a commit certificate in each cluster, they will broadcast it to everyone. And the reason that we send just to 2 nodes in this image is that with the cluster sending problem that Jelle has described in the previous session, we are trying to reduce and have minimal communication between clusters. So the primary of each cluster will send to F+1 node in the other cluster, so at least one non-faulty node received the commit certificate, and that one node can broadcast its commit certificate to everybody else, and that in this step everybody will have the commit certificate, and all those signatures of commit from the local consensus of the other cluster, and at this step they can order the transactions and execute them and reply back to the client. You should notice that this GOBFD is a full replication in all clusters. So all clusters have the same data, and all of them replicated the transactions of all clients in all clusters. The point is that we have reduced the inter-cluster communication by grouping these nodes to clusters. And the proof of safety and liveness is also available in the paper. You can find the paper in the VLDB website, and if you're interested, you can see the paper, and all the proofs and everything is there to understand this. And GOBFD in summary would be to ensure a common ordering, we are using linear communication between the clusters and the primary of each cluster, create those commit certificates, and minimally send it to the least node that they can send, that theoretically proven that they can send. And these certificates guarantee that the transaction has been reached consensus in the other clusters, and there is a view change protocol, which there are actually 2 view change protocols for replacing primary. One is a local one, which is same as PBFD. If the primary is not being PBFD in a local PBFD, they will change the primary, and the other case would be a primary that will prevent sending commit certificate, and we have a remote view change protocol for that. It's also available on the paper, and it's out of context of this tutorial. And yeah, that's it. And at last, we did the scalability test for the GOBFD, and as you can see, ResDB or GOBFD is performing far better than all other protocols, and this is also because of the parallelism of consensus in each cluster. As we add the clusters, the throughput will also go higher. And now here, I think the GOBFD slides are done. If anybody have any question, you would be more than welcome.
I think we have one question in the chat from Kaiwen. Is it possible for a Byzantine node from one cluster to migrate to the other cluster during a view change?
I'm actually not sure. Am I understand that correctly? But by migrating node from one cluster to other cluster, I think that's impossible, because the nodes are from the starts are assigned to each cluster, and they cannot change their clusters. But if somebody sends a message from one cluster to other cluster, they will simply ignore that, because they just expect messages from the primary of other cluster and just commit certificates.
And also,
let me add to what
kind of, yeah, go on, Suyash, say that.
Okay, thank you. Let me add to what Sajjad just said. So this is a very interesting question, and But there's a key requirement in GeoBFT. We expect each cluster to have a 3F plus 1 replicas. And that means each cluster can only have F bounded failures. Now, if you're going to move one Byzantine replica to another, then it is possible this balance might get changed. So that is a key requirement we want. We want every cluster to have 3F plus 1. So moving dynamics is not wrong. I mean, you can move one Byzantine replica to another, but then you have to shift another from somewhere else, or someone there has to stop acting Byzantine, because we want this 3F plus 1 to be always there. At least that is the minimum requirement we expect in GeoBFT. Yeah, Mo, you can go for it.
Yeah, so I mean, that's just sort of kind of also, as Suyash was saying, and Sajjad, this basic primitive of PBFT is that within the sort of one round or during the execution, you cannot switch, because otherwise it's going to be double counting. Because if the malicious, if there was one node that was malicious, the state is already diverged, and all of a sudden we say right away switching it to another node, well, that node has a malicious state. Now a new node is going to have also malicious state, so you're going to violate the F as well too.
Yeah, I understand. But the idea is that in a non-clustered system, the 3F plus 1 is calculated over the total N machines over, whatever geographical region. So now you're going into a 3F plus 1 within each region.
Yes.
But so it's a smaller number.
Less resilient. Yes. So it is less resilient. So any protocol that will do sharding or clustering, if you have 10 shards or 10 clusters, your resiliency is essentially going to be kind of divided by 10.
Okay.
So
it's
going to be divided by that factor.
If you had a mechanisms to address that and ensure that you can load balance the Byzantine failures, so to speak.
Yeah, you kind of have to assume the independence, sort of also.
I see.
Independence of these, and that's a very difficult problem. I think that's definitely probably a major theoretical open problem.
Because one thing that could really help is if you had a way to, because since you're using geographical clustering, so if you had a way to generate a proof of physical location, so then you have to stay in your cluster. You cannot just freely migrate, because that's how malicious attacker can coordinate, if they can freely migrate. But if you're bound by your geographical location, it won't be so easy for you to migrate to another cluster. But that means you would have to be able to generate a proof of location. I don't know how that would be possible using latencies, maybe.
Well, so that's another interesting point, Kevin. The malicious entity across cluster, they can collude. We're not putting restriction on the collusion, among those. So that's fine. They can. If you're malicious, doesn't matter where you are. You can assume all of them can communicate with one another.
Yeah, but then if they can collude and then they can overload one specific cluster and take it over.
Yeah, but here is the point. Once you are a node from the setup of the system, you have a public key, and everybody knows that this public key is from that cluster, and you cannot change your cluster during this. Yeah, you can collude, you can send messages to other nodes in the other clusters, but they will drop your message because it's not commit certificate. The only thing accepted from the nodes from the other clusters are commit certificates.
Yeah, but that would mean that your system can never grow. It can never accept new keys.
No, the growth of the system is not restricted, right? We can have the size of cluster increasing. I start with each cluster having 3F plus 1 equal to 4, F is equal to 1. Tomorrow I can have F equal to 2, that is 7. Then I can have F equal to 10, that is still equal to 31 nodes in each cluster. I mean, the only requirement is each cluster should have 3F plus 1 falling. That does not mean clusters cannot scale. There should be always F bad people in the cluster at any point of time.
So in general, Kaivan, with respect to comparing to PBFD, in PBFD, adaptation of adding node, or the fact that the node toggle between malicious and non-malicious, those characteristics that the PBFD has we also have we have the exact same guarantee. The only difference is that in PBFD globally you could have F independent failure, but in any geoscale or in general any sharding protocol, within each shard you could have a sort of shard version of the F failure, and that F typically, if you just sort of evenly divide your replica among shards, and you have let's say 10 shards, then the failure between every shard or the failure between every cluster is going to be smaller. Let's say the factor of 10, if that was the number. But in terms of adaptiveness, adding, removing nodes, or reconfigurability of adding or removing nodes, or the property of when node can switch becoming malicious or non-malicious, and what you mentioned, those limitations equally apply to PBFD, and any solution to PBFD, well, most likely will also satisfy it, but we're not touching those properties. Those properties are remain the same as PBFD.
Yeah, I guess you have to be careful when you're choosing your F in that case and the number of shards that you're gonna support, so that this is a safe limit for you. And then since it's a more sensitive number now, since you're not computing at the global scale.
Yes, yeah,
that's another thing is careful.
Yeah, absolutely, and that's another, I think, general interesting problem to any clustering and sharding. And again, the other thing is kind of going back to the first session, the cluster sending problem equally applies here. So the cluster here, the way they communicate reliably goes back to the CSV, the cluster sending problem that we talked about last time as well. So another instance of that is, which actually we directly utilize in GeoBFD2.
Okay. All right. Telman, I'm not sure how are we doing on time?
So I think, let me find the time. I think we have 2 minutes left officially.
Okay. Let's see how much can we do. At least we can try to do something here. So yeah, okay. So basically we'll want to introduce finally as part of this whole tutorial a permission blockchain fabric that we created, which we call as Resilient DB. And the whole idea was to design an open source fabric which can be used for fostering academic and research, industrial research. And basically the whole idea is this is a very simple and clean fabric. It does not have like complex components like Hyperledger. It can be easily extensible. You can add your own consensus protocols. And the key insight is everyone claims blockchain is slow and everyone says the consensus is the issue, but we believe there is something more. And Resilient DB recently got accepted at ICDC 2020, and we are also having a VLDB demo and tutorial on this thing coming soon. So yeah, let me try to explain something about Resilient DB before we end. So why should you choose Resilient DB? Well, Bitcoin and Ethereum, they have very low throughputs. They have 10 transactions per second. Then we saw a lot of existing blockchain databases. They claim throughput is 20,000 transactions a second, not more. And traditional databases have throughputs of 1 million transactions. How can we reach somewhere in between? We cannot work with such low throughputs. And everyone claims that consensus is costly. But we believe apart from consensus, there's something more. The system design itself is very important. And we believe there isn't exactly a study which is talked about, hey, how can you make system more efficient? And that is the whole focus about Resilient DB. We try to implement well-researched database and system practices which have been told again and again by practitioners and researchers in past many years. We try to apply them in our permission blockchain fabric. So to do that, the first step we do is that we actually take existing permission blockchain systems and we try to dissect them into parts. And we try to see what is that which is actually affecting their performance. We saw that most of them have a single threaded design. Why should you have a single threaded design when there are so many cores? I mean, if you are going to have a single thread design, then it will obviously reduce the performance. And a lot of these talk about successive phases of communication, consensus, like WhatsApp. It's good, but you have to just wait. One prime has to wait for the next. But there's a clear opportunity. You can do much more. You can parallelize things. Ordering and execution, they're just integrated into single component. You can easily split them into multiple threads or give even to different replicas. Then a lot of them talk about strict ordering. You don't need to do strict ordering. You can actually delay ordering until execution. And then there's a component called as memory management. Basically, everyone tries to do memory management directly in the storage. Maybe you can use on-chain memory to gain more performance. And everyone in blockchain community talks about just using distrust signatures, but can we actually use max? Do max give high performance? So there were a list of insights that we see in this paper, and some of them I've tried to summarize here. So the whole focus is a simple sentence. Can a well-crafted system, which uses a classical slow BFT protocol, slow which everyone calls, can it actually outperform a modern protocol? And that is what we try to show. Here we are Resilient DB, and we make it use PBFT. And this is another permission blockchain fabric, and it uses ZZIVA. So ZZIVA is one phase linear protocol, and PBFT is 3 phase. 2 of the phases are quadratic. And clearly Resilient DB performs much better than ZZIVA. And why does that happen? Because we have tried to implement some of the insights which have been already said again and again by the community. So this is the architecture of Resilient DB. We try to parallelize things, we try to layer it up, we try to separate each layer and start to divide the tasks. Crypto units perform the cryptographical tasks. They can be accessed by execution layer. There's an ordering layer, and we have a lot of threads which sort of divide the work. At the storage layer, we try to maintain the blockchain and the metadata. We try to use in-memory databases and all to get more performance. And then we have a lot of separate queues. Each thread has its own queue. Some threads might share the queue, and there's different threads are going to perform different tasks to achieve more performance. Basically, in Resilient DB, for each replica, we give it a specific architecture. We try to, for every task we'll see, and like for example, just we took this PBFT. In PBFT, we saw primary sends batches, or primary sends pre-prepare message, and then every replica sends the prepare message, and everyone does the commit message, and then finally execute. If you'll see here, most of these things are happening in parallel. A lot of these things are getting pipelined. And that is what our intuition is. You don't need to do everything in a single flow. You can actually parallelize tasks. There can be different tasks which actually create batches. There might be different threads which actually execute transaction. Some threads you can use for actually garbage collection, different threads for input and output, and then there will be worker threads which actually run the protocol. In fact, we discussed some time back a protocol called the multi-BFT, and the whole idea was to use Z instances. If we use the traditional architecture, then we'll actually have Z, there's no C parallelism happening, and here we can have Z parallel threads to get more performance. That is the whole idea of Resilient DB. So to start with, we'll just show a very simple graph. And that is where we'll try to show that can there be versions of PBFT we can actually perform better than ZZIVA? How do we do that? Well, we'll assume a system, and there's something called, you'll see in this graph, E and B. E means execution threads, B means batching threads. We start with a system where there's 0 execution thread and 0 batching thread. And we run both PBFT and ZZIVA. Of course, in this case, if you just have 0 execution and 0 batching threads and there is only just one thread, then obviously PBFT performs slower than ZZIVA. But if you'll see, even the throughput is quite low. Now, I add one execution thread. There's still no batching, only execution is adding. And the throughput is increased somewhat. Clearly, this one execution thread version of PBFT has already started outperforming some cases of ZZIVA already. Now I go further. I basically add 2 batching threads instead of just 1. Now, when I have 2 batching threads, in this case, the performance, I added 1 more batching thread and 1 execution thread. This version of PBFT has already outperformed 2 versions of ZZ1. Obviously, there's a ZZ1 version which has started performing good. I'm not saying that, but the whole point here is that this architecture at this point in time is quite better to existing architecture. And if we continue further, we add more batching in threads. Basically, we may add more parallelism. Just see, this version of PBFT beats all existing versions. So we all know parallelism helps. And this is the clear point which we were trying to show, that it's not just the consensus, it's also the design which matters. And just using a good design can actually help perform even a slower protocol better. There are few more insights. We saw that how can batching improve performance? There are some papers who say that batching actually helps gain performance. Always? Really? Not sure so. There are some papers who say that batching is not good, it might be very costly. So we did some experiments and we saw that batching is actually useful to some point in time. Just after some point in time, it actually saturates and reduces performance. So basically, there's the whole point that you should find the optimal point where the performance is actually good with the batching. Then we thought of checking what are the memory gains you can get. Can actually having in memory better than having a database? Well, clearly, use as much in memory as possible. You can gain so much of throughput. Then we thought of checking with number of clients. A lot of these systems run just too many clients or too less clients. What is the effect? Well, if you increase clients to a very large number, then throughput will not actually increase too much. You will have till some level, and then after that, it sort of saturates. But there's a clear increase in latency. So we need to find an optimal number of clients a system can actually handle. So these are only 4 insights right now, which we show in this presentation. But we urge you guys that go ahead and look at the paper. And in that, we have shown at least 10 to 12 such insights on different parameters. So yeah, I mean, this is what whole idea of Resilient DB was. Although we are lacking time, but our next idea was to basically make you all guys, whoever is interested, basically make them play with the hands-on of Resilient DB. But I think I'll pause at this moment, and if anyone has any questions or whatever the chair says, we'll go do next.
So I have a quick question.
Kusama, go ahead. Yeah.
Yeah. When you said that you did batching, right, to improve throughput, did you trade off by doing this? Did you trade off throughput for latency?
Let's go to the batching. Yes, we did. We did that, but not much, right? If you see, there are already some cases where batching actually helps even latency. And now that's a very interesting question. So now, if you're going to measure throughput of one request by one request, then obviously batching there will be whole cost of batching, because the whole idea is that if there will be a sequencer will actually sequence all the requests. He basically create a batch and then he'll send that batch. That is true. But now if you're going to use pipelining, in these results, what we show is that effective pipelining, and you can by employing batching, you can actually even lead to a reduction of latency.
Right. So by effective pipelining, it effectively increases the concurrency rate.
Exactly.
Okay, thanks.
I mean, just also to add to that, I mean, in general, as you said, the batching will increase the latency, but if you assume that you're only going to get one request at a time and you're not going to get another request till this is completed, then you can really minimize the actual latency, and that's what hot stuff really does, and they can only do sequential consensus. But if assuming you have a lot of requests coming in, as you now shown here, is that you're much better off to batch them together and do one consensus for a whole set of transactions, as opposed to kind of do one at a time and your queue sort of growing and waiting on.
Right. Thanks, man.
Essentially, that's blockchain, right? I mean, that's what it's doing. It's batching transactions and make.
Yeah.
All right.
Okay, so I guess we can continue for a bit because there's no other session after this. So if you want to show something, or anybody wants to do this hands-on.
Definitely.
Please go ahead.
Sajjad will continue. Thank you.
Yeah, I can go over it very fast. Definitely. Let me share my screen with you. So yes, thank you everybody. Now I'm going to talk a little bit about the resilient DB blockchain platform that we have implemented in C++ that can that allows you to implement any consensus BFT consensus protocol or any blockchain protocol in it and experiment it with different parameters. The first, you need to go to the resilientdb.com. The paper that Suyash was explaining before is there. The link to the GitHub is there. And yeah, in order to use it, there are simple ways that I'm going to explain. Sure, yeah. There are two ways to run ResilientDB. The first one is using Docker, which helps you to run ResilientDB on one machine and exploit having containers for each machine. But the results that you get from the Docker would not be accurate because the resources are being shared between the containers. The other one is using actually physical machines as nodes of your blockchain system, which have separate scripts for both of them. In this tutorial, I'm going to just explain how we use Docker for running ResilientDB. And the first step is to clone the code. I have cloned it here. Yes, ResilientDB. And can you see my terminal? Is it visible?
Yes.
Yeah. And in order to run it to see a very small demo, you just need to use the ResilientDB Docker scripts and specify how many clients and how many replicas you want. I will explain more parameters afterwards, but first I just want to show you how these machines works on the Docker. When you run this command, it will create a Docker container for each of your nodes that you have specified. And after creating these machines, it will create a config file based on default ones that are also adjustable. I will explain how those parameters can be changed, and after that it will compile the code. And as you can see in this step, the code is being compiled. After code gets compiled, it will distribute the binary files of the clients and servers to the nodes in Docker containers, and it will be start running. Meanwhile, I can show you the results. Yeah, after it will, after the code is been run, I will show you afterward. Here, the nodes, the 5 replicas are being run here, and also 2 clients. They would be run for 1 minute of warm up, and in the warm up section, no transaction would be counted, no throughput will be counted, and after 1 minute warm up, it will run for 2 minutes and count everything and show you the stats. But everything is adjustable. You can change warm up time, you can change run time, everything. But let's go straight to the results. And after running those nodes, you would see a page like this as results. In the first 5 lines, you can see the throughputs of system. And as you can see, in 4-core machines that we are using with Docker, we got 38K of transaction per second, and average latency of half of second for those ones. The next one, the next lines are the idleness of thread, the amount of usage that we got from each thread. In the previous part that Suyash were explaining, we had batching thread, we have execution thread, we had checkpointing thread, we have worker thread, and these ones are the idleness of those. For example, if you can see in the first node, in the second, in the last third node, the batching threads are 0, which means they are not doing anything because the batching is happening at the primary, which is the first node. And the last node and the last thread is the execution thread, which has the least idleness here. And yeah. And you can see the memory usage of the system at the last lines. As you can see, 150 megabyte of memory is being used for each of these things. Yeah, it's still being run. The next part will be explaining how PBFD fits to Resilient DB. As you know, PBFD has 3 main phases. By adding the client reply and client request, it would be 5. The first one is the client request that I will be explaining. Before that, I want to show you the structure of our main thread, which is initializing the queues, initializing the transport layers that all are transparent from your perspective of view. In order to design your protocol, you just need to define the messages and the workflow. You create your own messages, you define your own flow, and you use our transport layer, message layer, and execution layer of our system. So for PBFD, we have the client request, and for each type of message, we have a corresponding function to process that message. For example, if we have a client request, we will be having a function to process that client request. If we have a pre-prepare message, we will be having a process prepare message. And all these steps are simply by creating message class, inheriting from the base message class, and just defining a function, and do whatever your protocol requires from that transaction or from that request. And as you can see, the code has been run here completely, and we have the throughput, latency, as all these things that I have shown you in that slides. And also the summary would be saved in a file called res.app. This is a very simple version of running it. This is just for a demo purpose. In order to implement and develop things, it would be better to run it on actual machines and see the results on the fly. In PBFD, I explained the client request, and after that, it would be a pre-prepare message which corresponds to the batch request in our system, and there's a message and there's a process function. These two corresponding messages and function. And we also have that for the prepare and commit messages. And as you can see, the code has been completely commented. You can understand what function is doing what exactly. And at the end of commit round, there would be execution. And that's also have an interface to create execution messages, which you can easily find in a code that I'm not going to deep dive into it. Yes, and in order to do all those pipelining that Suyash were explaining using parallel design, we need to have lock-free queues. We need to have queues and multiple threads to do different things. We have a class called work queue, which uses the boosts lock-free queues, and that's also a very important part of Resilient DB that makes that helps Resilient DB to create this parallel architecture, but you do not need to, in order to implement your protocol, you do not need to touch this. This is completely service out of independent of any consensus protocol that we have implemented, but it is important for us. We also have input and output threads and transport layers. They are also completely isolated, and you can do whatever adjustment you want in the transport layer, but if you want to just implement the protocol, those are all there and safe to use. And at last, I just want to share you a very tiny part of parameters that we have in our system that you can find in config.h file, a file that was created by the ResilientDB Docker script. But if you want to run it yourself, you should change it manually by your hand. The first one is the node count, thread count, client node count, max transaction in flight, which is kind of the client, the number of messages that each client can send before receiving the response. So it's kind of an adjustment parameter to not kill the system with, not overwhelm the system with your messages. Number of batch thread, batch size, how many, how frequent checkpointing protocol should work, using different types of crypto, for example, RSA, ED2, CMAC, MAC, and all these parameters that you can use, that you can adjust and use in the ResilientDB. And thank you. Sorry, I was going too fast because we were out of time. If you have any question, you can ask here, or if you find any interesting thing in ResilientDB, you can clone, you can create issues, you can fork, and we can interact also on GitHub. Thank you, everybody. If there's a question.
Yeah, sorry, could you share the GitHub? I will we'll post it on the website of DEBS.
Yeah, definitely. It's resilientdb.com, and the code, everything is available from there. But yeah.
Okay, perfect. Thank
you.
you.
Thank you. So I will give the speaker to the chair. Thank you very much.
Okay, so thank you very much for the tutorial and also for the insights into ResilientDB. And so if there are any further questions, reach out to the speakers now. We also still have the chat on Slack, so we can asynchronously continue to discuss there. And if there's no further questions, then in general, I would say thank you very much for the presentation. And
all right, thank you, everyone.
Thank you, everyone. Thank you.
So thanks everybody today, Tillman, Mo, Sajjad, Suyash, Jelle, for the tutorial, and we'll see you all tomorrow. So it starts at 9 a.m. On the East Coast, 6 a.m. on the West Coast. It's a little bit early for you guys, and 3 p.m. in European time. So we'll have the opening speech of the main conference and the first keynote by Tamara also. Thank you, everybody.
All right, thank you.
Thanks, Karen. Thanks, everybody.
Thank you.
Thank you. Bye-bye.